All right, hello again. We're going to continue with Chapter 9, moving on to Section 2. We're going to break Section 2 up into two different parts. And so today we'll talk about conservation of momentum when we have one-dimensional collisions, and then the next part will be two-dimensional collisions. So let's look at some two-particle collisions. All right, well, Newton's third law says that for every action has an equal and opposite reaction. And so even though the sizes and the velocities of two particles can be different, the forces that they exert on each other are equal and opposite. So when we talked about Newton's third law initially, we talked about like an apple falling. So Earth pulls on the apple, which causes it to fall down. But at the same time, the apple is pushing back on Earth, but Earth doesn't spin out of orbit because of the size difference between the apple and the Earth. But even though the sizes and velocities of those two objects are different, the forces that they exert on each other are equal and opposite. And this leads to our law of conservation of momentum, which relates to how the force of object D on object C is equal to the negative force of object C on D. And so we have the interaction pair of two forces acting on each other, or acting on the different objects. And so this can relate to impulse and momentum. So impulses are also equal in magnitude, but opposite in direction. And so the time intervals over which the forces are exerted is the same for both objects. If we apply these forces, it's going to be exerted for the same time with both objects. And so this, since we know that change in momentum is equal to impulse, then the sum of the momenta of all the objects, we're going to look at like cue balls and playing pool, and so the sum of the momenta of all the objects is the same before and after a collision. And so that's the system that we're going to look at when we look at conservation of momentum. And so the momentum gained by object D is equal to the momentum lost by object C. And so we're going to look at a lot of cue ball collisions with other pool balls, and so the momentum gained by the object that gets hit is equal to the momentum lost by usually the cue ball. Okay, so law of conservation of momentum says that for, let's say, object C, we know that the momentum final for object C minus the momentum initial, which is the change in momentum, okay, so change in momentum of object C, is equal to the impulse, which is the force of object D on object C times the change in time over which that force occurs. And so this is just the equation that we talked about the other day with the impulse momentum theorem, and now we're going to relate that to our conservation of momentum. For object D, we could say the same type of equation. The change in momentum for object D is just equal to the force of object C on D times the change in time over which that force occurred. These changes are equal and opposite, and so the forces are also equal and opposite, and that's how we're going to relate this to the law of conservation of momentum, because if they're equal and opposite, then momentum is conserved. There are a few conditions that need to be in place in order to have conservation of momentum, and so we need to have a closed system, which means the object won't gain or lose mass. Now, a lot of times we're also going to talk about car crashes and things like that, other collisions. We're going to assume that even though we know pieces can fly off the car and things like that, that the object's not going to gain or lose mass. So it's a closed system. We're going to draw a circle around it. We also have an isolated system, meaning we only have internal forces. There are no outside forces acting on the system by objects outside of it. And so we're basically just going to draw a circle around our collision, and that's going to be our system. And the reason that we do this is very similar to why sometimes we ignore air resistance. It just makes the problem more complicated, and we're trying to just look at that momentum piece. So law of conservation of momentum says that the momentum of any closed, isolated system will not change. And so we're going to look at how variables change within that. Okay, as long as our momentum final equals our momentum initial, the velocities and things like that can change within that system. And that's what we're going to look at. Okay, so a common example is recoil. So let's say that we have two skaters and they're standing there. So the momentum before one skater pushes the other is 0 because they're at rest. And we could say that another way to express the overall momentum for the system would be the momentum of object C plus the momentum of object D initial. So let's say C and D are two different skaters, or people on roller skates. Okay, but we know because they're both at rest that the momentum is going to equal to 0. And we can also look at the final as being momentum of object C final equaling the mass of object C times the velocity of object C final. And let's say we want to know some information about that. So we want to know what is the final velocity of object C. Okay, well, after the push, since before one skater pushed the other from behind, they were both not moving, and so the momentum initial was 0. Well, that means that the momentum final, or after the collision, must also be 0. And so we can look at this as the momentum final of both objects added together. And since we have momentum of C final here, that's equal to negative momentum of D final. Because we're saying that momentum before the push was 0, which is equal to the momentum after the push, which is the momentum of object C plus the momentum of object D. Well, since this is 0, I can rearrange by subtracting object D from both sides, the momentum of object D from both sides, which gives me momentum of C final is equal to negative momentum of D final. Remember, momentum and impulse are vectors, so direction does matter here. So what this means is that momentum of both objects are equal and opposite. We can break down the momentum equation into mass and velocity, and so final momentum of object C is really equal to the mass of that object times its final velocity, and that is equal to the negative of the mass of object D times its final velocity. And if we know 3 of these variables, we can solve for the 4th. So for example, if we usually will know the mass of both the objects and the final velocity of one of them, and we could find the final velocity of the other using this conservation of momentum. So the velocity of the skaters will depend on their masses. Okay, if you have a very small skater trying to push a larger skater, that smaller skater is probably going to experience more of a velocity because its mass is less. We need to know some forces, so how hard did object D push object C, and then we can break down that momentum into these velocity and mass equations to solve for different variables. Okay, so we know that forces are equal and opposite, and we have to have this interaction pair. Well, what about something in space where there's really no forces? How does a rocket propel itself when it has nothing to push against? Okay, well, the way that rockets work, the rocket and the chemicals are a system, because remember, for conservation of momentum, we need to have a closed and an isolated system. And so we've got the rocket, but we also have all the fuel, and that's going to create the gases that the rocket can then push against, and those are going to create our system of forces. So the forces that expel the gases are internal forces. So we have this combustion reaction, we produce these gases, the gases push against the rocket, and the rocket pushes down against the gases, and that's what propels the rocket forward. So momentum is conserved for the rocket in space due to that internal system. Okay, so we are going to go over these problems in class, but please feel free to attempt them on your own if you want, and then here's the homework. So we'll be doing a PhET lab for this first part, and then after we discuss two-dimensional collisions, we'll work on some homework. Have a good day.